We're just going to be going over very kind of in what I hope are the most simple terms, the physics of sound, in particular sound waves in strings. So I'll be kind of talking about the physics of guitar or violin or other stringed instruments, but a lot of what we say applies to other musical instruments and other sound phenomena. So first of all, I want to define a few things. I'm going to share the whiteboard. When we have sound travels in waves. So we can think of it kind of like this. If these could be pressure waves in the air, so when I clap my hands, then the pressure goes up and down, up and down, up and down. That up and down oscillation of pressure hits our eardrum, makes our eardrum vibrate at the same rate, the same frequency, and that gives us our perception of sound. But this applies to waves of light, it applies to waves in water, a lot of what we're going to say today. So we characterize a wave as having a wavelength. So that's literally the distance between the peaks of the wave. And this wavelength, we use the Greek letter lambda for it. It looks kind of like a Y that's upside down. Okay, it looks like a lowercase letter Y that's been turned upside down. And how we can characterize it from the peak to the peak, or from the trough. The bottom of a wave is called a trough. T-R-O-U-G-H. These are the peaks. We can also characterize the wave by looking at where it crosses the middle, but then we have to be a little more careful because the next time it crosses the middle is only half of the wave. So if it crosses the middle going up, we look for when it crosses the middle going up again. Okay, so this distance is also lambda, and this distance is also lambda. So that's if we would freeze the wave in time. Like if we have a wave in a string and we take a picture of it with super high speed camera so that it's not blurry, then we would see a picture. We would see a picture that looks like this. And so we would be measuring the distance between the peaks. That's the easiest, or the troughs. That's the easiest thing to do. But if we let this go in time, like we let it go, what's going to happen is after a little while, it's going to be smaller. It's going to look something like this. And then after a little more time, it's going to be flat. And after a little more time, it's going to kind of flip and go the other direction. And after a little more time, let's try that again. No, and so if we're looking at this, because it usually vibrates quickly, we see kind of a motion blur, and we see a lot of peaks. Okay, it looks like a lot of peaks. At any moment in time, only half of those are peaks and the other half are troughs. Are you kind of following what I'm saying? But because it's moving so fast, we see the full sort of just looks like the string gets fat and then it gets thin. So when we have these fat areas, these are known as antinodes. And the areas that don't move, that just kind of look like fixed points, are known as nodes. Okay, so that's what it looks like in time as it blurs. Now, if we had a really good high-speed camera, we could actually record how long does it take to go from where this is a peak to where it's a trough and back to a peak again. So if we watched one part of the string, we could time how long does it take to go from the top position to go down and back up. So that time is known as the period of the oscillation. So how long does it take for one piece of the string to go down and then back up, from the highest position down, all the way down, and then all the way back up? And we usually say the period is T, capital T, for time period. And the time period T is equal to 1 over the frequency. So the frequency would be, instead of how long it takes to make one complete oscillation, it would be how many oscillations it makes every second. So if it takes, a 60th of a second to make an oscillation, then there would be 60 oscillations per second. So it's kind of the inverse. If the period is 1/60th, then the frequency is 60. Now the units for frequency are called hertz. That's just a second to the -1, hertz, H-E-R-T-Z. And when we are learning about frequencies, when we see a problem, it usually expresses that frequency in terms of hertz. So, for example, if we play, if you're in a symphony or an orchestra and you're tuning your instruments, they typically tune to a certain pitch tuning fork. And that tuning fork is 440 hertz. That's an A, a 440 hertz A. That is standard. Although we know, because we found old tuning forks from several hundred years ago, that over time, people have been tuning sharper and sharper and sharper, because being a little sharp sounds a little better than being a little flat. And so people err in the side of being slightly sharp in sound. Lauren.
What's the period again? What'd you draw?
The period, you can't really draw it, because I'll show you a simulation in a little while. It's how long it takes for the wave to go from its highest position down to its lowest position and then back up again. So it's kind of one complete cycle. I have a simulation that's the same simulation you'll see in the lab, and I'll use that in a few minutes to kind of illustrate and let you visualize some of this. Okay, so finally, then how are frequency and wavelength related? Oh, Christina, question?
Is that definition of period just the same as like sine, cosine, tangent period? Or does it mean something different?
So if you have something like sine of x in math class, okay, so the period of the oscillation it's a little confusing. The period is this distance. That's how long it takes. But I don't want to confuse it. This is a graph. And so what you call the period in math class is more like the wavelength. This graph is moving. That's the difference. This is moving. So it's not the same. I don't want you to confuse those two things. Okay. So the velocity of the wave is just the frequency of the wave times the wavelength. Now, the speed of sound is typically quoted as 340 meters per second. It really varies a little bit, but you'll see this number in a few of the homework problems. That's the kind of textbook number for the speed of sound at standard temperature and pressure. And because the speed of sound is fixed in air, the higher the frequency, the lower the wavelength. And the bigger the wavelength, the lower the frequency. They multiply together to get a constant, so they're inversely proportional. Now, let me use my guitar to sort of let us hear the difference between different frequencies, okay? So a high frequency, my thin string, that's my high E string, that has a high frequency. And my low string, that's also an E, but it's 2 octaves below. It's a lower note, so that means smaller frequency. Okay, so in the guitar, the speeds of the waves in each string are different because the wavelengths are all the same. The wavelength is related to the length of the string. So we're going to be talking a little bit about the physics of what determines the speed, you know, not in air, but in a string. Okay, in a string, it's a little bit different. But for now, I just want you to hear the difference for a given speed in the note. Here's an E. That's a low frequency. And if I make the string shorter, I get a higher pitch, you know. So the way a guitarist is, or a violinist is making different notes, different frequencies or different notes, is by just changing the length of the string. We cannot change the speed of the sound in the string very easily, not like while we're playing. So the only thing we can do to change the frequency is to change the length. So you kind of, I don't know if you can see. Can you see this? Can you see the guitar? No? Let me see if I can. Okay. All right, so you can see it now. So notes, if I don't touch the strings, that's the sound they make. If I shorten all of the strings, it makes a higher pitch. I have a device here called a capo that some guitarists use to just be lazy and make all of the strings short. And that sounds, you know, higher pitched than. So you can change the key by just adjusting essentially the length of your guitar. If you think of concert, you know, instruments, a cello has longer strings than a violin, and because of those longer strings, it makes a lower pitch. So, okay, so let me put the whiteboard back up, and I'm going to talk a little bit about, you know, what other things control the velocity of the sound in the guitar. Okay, so are any of you? Do any of you play an instrument? Sumner, what do you play?
I played the cello.
Okay, so do some brainstorming. What are the things that you can do to make a string higher pitch? What property of the string makes it higher pitch? What do you do to make it higher pitch before you even start playing? Like when you're tuning?
I mean, that's just like putting more like making it tighter.
Yeah, and the tighter it gets, what happens to the pitch?
The higher it gets.
Okay, so it looks like the velocity, well, let's just say the frequency is kind of proportional to the tension. It turns out it's proportional to the square root of the tension. What about the different strings? All of those strings have the same length when you're not playing it, right? But they have different notes. They all have the same tension, roughly. I mean, that's
around.
Making a cello makes it so that the strings will have roughly equal tension, because if they don't, the neck is going to warp. So what else do they change about the strings to change the pitch?
Just how thick they
The
are.
How thick they are. What did you say, Christina?
The elasticity of the material.
Yeah, so the elasticity of the material, not as much. It's more about just how heavy the material is. This is probably easier to see on a guitar. If I don't have my nylon string guitar here, but the fat strings, the low strings, the low E is a fat metal wound string, but the G string is also fat. It's just made of a different material. It's made of nylon, which is a less dense material. So it's proportional to 1 over the square root of mu, where mu is the mass divided by the length. So that's called the linear mass density. And, if you want the string to have a low pitch, you want to have a high mass density, meaning you want the string to be fat. Okay, so if you look at the strings on a bass, they're really fat. Okay, if you look at the strings on a violin, they're skinny. Of course, the length of the instrument is involved as well, because, well, the longer the wavelength, the shorter the frequency. So technically, it's not really the frequency that's changing with the tension and the mass density, it's the velocity. So the velocity is equal to the square root of t over mu, and that means the frequency, which is lambda over, velocity over lambda, is 1 over lambda times the square root of t over mu. So you can see then, the bigger the tension is, the higher the pitch, the higher the frequency is going to be. The lower the tension, the lower the pitch or frequency is going to be. The bigger the wavelength, the lower the frequency will be. And the bigger the mass density, the lower the frequency will be. So let me again, with the guitar, just kind of show you or let you listen to, if I reduce the tension, I've got a bass if I lower the tension enough, but then it rattles because there's not really enough tension. Okay, so the other thing about waves in a string, when I pluck the guitar string, it sends a wave down the string, and the string hits the end of, where the string connects to the bridge or the nut at the top end of the guitar. The wave reflects and it bounces back. And so technically, if I pluck the guitar string, those waves go both ways. They start reflecting back and forth, and they join up. And when they join, we get what's called a standing wave pattern. And I'm going to use the simulation from the lab to try to demonstrate what a standing wave pattern looks like. So let me bring that up. Okay, Christina, did you have a question? Your hand is up. No question. Okay, so can you guys see sort of a yellow simulation? Okay, so what we have here, there's a few different things we can do with this simulation. We can put manual movement of the string. So I can just grab this wrench and lift it up, and we're going to see a wave that just travels through this string. And if I have the waves going both ways, we start to see a pattern. We can see a pattern showing up. If we have the end being loose instead of fixed, when the wave hits the end, look what happens. It just kind of, let me kind of stop this. I'll give it a little wave. And that wave, when it comes back, it stays on the same orientation, whereas when it hits a fixed end, it flips. So that's something to observe that you'll notice in the lab. Now, if I increase the tension, look what happens to the speed of the wave. On the other hand, if I decrease the tension, the speed of the wave is much slower. Okay, we can also send pulses. There's an option to send a pulse. I just press the button, and I'm going to turn the amplitude up on that thing. So the amplitude is how tall my pulse is. Got low tension, got high tension. Okay, so we can watch what happens with the pulse. We can even use, a timer to measure the speed of this wave, because there's a ruler available to us that allows us to measure the length of the string. And so you'll be doing some of those things in the lab simulation. But the one that's the trickiest is the following. When I put it on oscillations. So this is when I kind of drive the string. I make it oscillate with something on the end that's oscillating. Now, the amplitude of my oscillator is really big, and that kind of makes for a crazy pattern. So I'm going to try to reduce my amplitude a little bit, turn up damping. Turning up damping is friction, and that kind of kills the wave. Then I'm going to turn the damping off, and we're going to see what we get. We get, somewhat chaotic patterns, somewhat erratic. Okay, if I change the frequency a little bit, I can see a more stable pattern. Now, this pattern is stable in its shape, but its amplitude is not stable. It's going to keep getting bigger and bigger and bigger. So I want us to have that visual in our mind. Even if I kill the oscillation and I turn the amplitude way down, so this little oscillator on the end is doing very little. It's moving only up and down a little bit. We're going to see that the amplitude is going to still become very, very large, even with a small oscillation. So when that happens, that means we have found one of the standing wave patterns, one of the standing wave frequencies. Okay, notice how the amplitude of my wave is getting very tall. I can put a reference line in here, and I can use that to sort of see, is it going up, or has it stopped going up? This thing is still getting bigger and bigger with every oscillation. So that means I'm pretty close to one of the special standing wave frequencies. If I change the frequency, we should see a different pattern. Let me kind of kill that first pattern and then see what happens. So here I'm seeing kind of, if we pause it, there's a peak and a trough and a peak. If I had that whole picture with nodes and antinodes, there would be this first hump is an antinode, the second one is an antinode, the third one is an antinode. So this would be a standing wave with 3 antinodes. If we could play it fast enough to see motion blur. And I'll go back to the whiteboard in a minute and draw some pictures to try to connect this with some physics. But if my frequency is not right, let's see this frequency. It looks like I've got three kind of humps. But let's see if they're stable and if they grow. Oh, see, it's kind of dying a little bit. Then it starts to get bigger, and then it dies a little bit. So even though this looks a little bit like a standing wave pattern, it's not, because it never gets big. The biggest it gets is something, like that. So you're going to be looking for these standing wave patterns. And by doing that, you're going to have to search around, changing the frequency a little bit. This is the frequency I had before that looked pretty close. You know, this is getting big pretty rapidly. So this is definitely closer to the right frequency than what I had before. Maybe it will be even closer if I notch it down a little bit. And that's what this reference line is for. I can sort of see how high it's going. Let me turn the rulers off. Okay, 120 is definitely not, 1.20 is not as good as 1.21. Let's put it back to 1.21 and see what happens to the amplitude. Does it get bigger? It does get bigger. It's crossing my reference line. So maybe 1.22 is even better. And so on. So this is a kind of a fine-tuning process. It takes a while. You have to let this thing go and try to see when. Ideally, I want this oscillation to go off of the page. Okay, I want it to get so big that it goes off of the page. So I'm still not quite there yet. Now we could make it get bigger by turning this up, turning the amplitude way up. And if I do that, I will think that I found the standing wave because this is so big. But it's not a standing wave. It's just that I'm driving with such a big amplitude. If I turn the amplitude way back down, turn up my friction to kind of kill that wave, I have to watch it and see, does it build up again from a very small amplitude? That's what we're looking for. Okay, so let me go back to the whiteboard, and then I want to connect this visual with some physics. Actually, before I do that, I can kind of demonstrate these standing waves a little bit with the guitar. So when I pluck the string, the standing wave I get is just the string goes up in the middle and down in the middle, and that's it. It has just one antinode, and it has then a fixed point on the ends. If I instead touch the middle of the string, so I'm not holding it down, I'm just going to touch it and pluck it. So I get the same note as if I actually hold the string. When I just touch the middle, what I'm doing is I'm forcing there to be a node in the center, which means I'm making the wave pattern, the pattern with two humps instead of one hump. And that's a higher frequency because it's a smaller wavelength. I can hold it in different places and get different harmonics. These are known as harmonics. In fact, any subdivision of the string, if I hold it at the midpoint of the string, I get a harmonic. If I hold it at the third of the way, I get a harmonic. If I hold it a quarter of the way, I get a harmonic. And they're scattered throughout here. There's infinitely many of them, in fact, but they get harder and harder to find. If I go for like a 16th of the length of the string, I could get a harmonic that would have 16 little humps, but it's very hard to pinpoint that exact location. So let me put the whiteboard up and talk about these harmonics. Okay. So these are standing waves. The reason they're called standing waves is because the pattern kind of stays in place. If I just send a wave pulse, we can see that pulse moving back and forth. So that's a moving wave. These are standing waves. The pattern just sort of flips up and down and it stays in place. If I have a string with a length L and I pluck it, I get the fundamental frequency. It just looks like this. The fundamental frequency is also known as the first harmonic. Do you ever do harmonics on the cello?
Yeah, I do.
Okay, so I love harmonics. They're cool. I actually use harmonics to tune my guitar, although for sort of weird technical reasons, it's not exactly correct tuning because guitars are actually designed to be slightly out of tune so that they are the same amount of out of tuneness as a piano, which is sort of a strange, interesting history of music decision that was made in the tuning of pianos. They're tuned slightly out of tune so that they sound not out of tune too much in any key. They're out of tune no matter what key you're playing in, but they're only slightly out of tune in every key. And that's because in an orchestra, it's too hard to retune a piano if you're changing the key of the piece that you're playing. So guitars were designed to have the same tuning as pianos. Okay, so the first harmonic is the first pattern we see. And technically, what we're seeing is only half of a wave. We only see the first half. The second half would be over here, but we don't see it because there's no string over there. So in this case, the length of the string is just 1/2 of the total wavelength. And we would say the wavelength is 2 times L. So it's twice the length of the string. If I hold the string in the middle, okay, if I have a string and I hold it in the middle, I touch it right in the middle and I pluck it right about there, then what happens is it forces there to be a node there. And so my wave does something like this. So in this case, the length is just the wavelength. We get one complete wave happening here. This is called the second harmonic. And if I hold it 1/3 of the way, I just make it have fixed points there, then I get a wave that looks something like that. So that the wavelength is really just 2/3 of the length. Okay. This is known as the third harmonic. And this continues indefinitely. We can get a fourth harmonic like that. Here, the wavelength is just L/2. And the sounds of these, if we double we cut the wavelength in half, we double the frequency. So the difference between my first harmonic and my second harmonic, the wavelength has cut in half, and so the frequency doubles. That means that's an octave. Okay, that's an octave. So with my guitar, if I play the low E, and then I play the second harmonic, that's an octave higher. The third harmonic is actually a B. It's not just dividing in half again, but the fourth harmonic is an E again. So E, 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 all E. So we're on the high string. Probably can't even hear that one over the speaker. So there's a pattern here if we look for it. Okay, what's the pattern? The wavelength is equal to 2L/N, where N equals the number of the harmonic. So what did we have before? We had 2L, and then this would be equal to 2L over 2. The next one is 2L over 3. The next one is 2L over 4, and so on. 2L over 4 reduces to L over 2. So there's a pattern for the wavelengths of all of the harmonics. And once we find the pattern, it becomes really easy to find the other harmonics. So how about the frequency? Frequency, times wavelength equals the velocity. So the frequency is the velocity over the wavelength, which would be the velocity over 2L over n, and that's the same as n times the velocity over 2L. The first harmonic frequency would be called F1. That would be when n equals 1. Let's call this F sub n. That's V over 2L. And so the nth harmonic formula is just the number of the harmonic times the frequency of the fundamental frequency, or the first harmonic. So in other words, if I want to find the new frequencies, if I want to find the frequency of the third harmonic or fourth harmonic or fifth harmonic, once I've found one of those frequencies, I just start multiplying, doubling them, tripling, quadruple. If you can find the fundamental frequency on the simulation when you're doing the lab, you can predict what the others will be. So let me go back to the simulation one more time. Okay, and let's just try this. So this kind of looks like the fundamental frequency. It might not be exactly right. I might have to go up to 0.42, 43, or down to 0.40. I'm not going to take the time right now to do that. But the idea is, if this is the fundamental frequency and I multiply it by 5, I should be able to find the fifth harmonic, the one that would have 5 humps. So if we multiply this by 5, that's right up in kind of this range. Let's just see what we get. Okay, so that does kind of look like 1, 2, 3, 4, 5 peaks. So this won't be exactly right, but it definitely gets me in the ballpark quickly, and then I can start kind of nudging the frequency up a little bit, down a little bit, and try to see, which frequency gives me an oscillation that eventually grows off of the page. It just becomes too big. Okay, so again, I don't want to take the time to do that because that's what you're going to be doing in your lab. This is probably pretty close to the fifth harmonic. Okay, so let me pause. I know I've been sort of just throwing a lot of information at you. Are there any questions before we do some examples?
So are we looking for the standing wave pattern when you say we're looking for when it goes off the page?
Yeah, that's how you identify it. When it's, you keep adjusting the frequency. It may not go all the way off the page, but it should be getting close. And then you get to a point where you nudge the frequency up a little bit, and maybe you start below the harmonic, you nudge the frequency up and the amplitude gets bigger. You nudge the frequency up again, the amplitude gets bigger. You nudge it up again and it gets smaller. So when it starts to get smaller again, you passed it. And then you've got to kind of back up a little bit and try to figure out which one was really the biggest. If you want to be kind of fast, you can do it in increments of like 0.1 hertz and sort of try to zero in. And when you see, okay, it was biggest somewhere either 0.1 or 0.2, maybe 0.15 0.50 or 0.60, then maybe you start trying 0.52 and 0.54 and 0.56 and 0.58, and you see which one really gets the biggest. If you get to the point where it's going off of the page and the input amplitude is really small, then you found it. Okay, let's try another example. Suppose we have a guitar string of length 64 centimeters. And mass, if we were to weigh just the 64 centimeters that's stretched between the ends of the guitar, mass 0.3 grams. What tension would we need to create a fundamental frequency of 440 hertz? Okay, so we know that the velocity equals the frequency times the wavelength. And if we have a guitar with a fundamental frequency, then the length of the string is really just half of the wavelength. So in other words, the wavelength is 2 times the length. So our fundamental frequency times, the wavelength is equal to the velocity of the waves. And we know from before that the velocity is the square root of the tension over the linear mass density, mu. So if we want to solve for the frequency, we can square both sides. Get tension over mu equals frequency squared times 4L squared. And to solve for tension, we multiply by mu on both sides. And remember that the mu is just the mass over the length. So one of those lengths just cancels out. Finally, the tension would be 440 hertz squared times 4 times 0.64 meters. Okay, so we have to make sure to turn L into meters so that all of our units work out. And then likewise with the mass, we need to put it into kilograms. So that's 0.3 times 10 to the negative 3. Okay, so putting it into kilograms is like dividing by 1,000. And let's see what we get. We get 148.7 newtons. Okay, so we could use that if we wanted to find what tension to get the third harmonic to be a certain value and so on. We would just need to determine the wavelength for that particular harmonic, and everything would work the same way. So let's try something a little different. Let's look at waves in a pipe. Okay? So in a pipe, we have air going through the pipe. You can think of like a pipe of an organ or a flute or something along those lines. And we get waves in the pipe. Now, typically we specify whether the pipe is open on both ends or closed on one end. So closed on one end would be sort of similar to like a bottle. If you blow across the top of a bottle, you get a note, you get a tone that would be the fundamental frequency of that pipe, even though its shape is a little different. Let's imagine that the pipe is closed on one end. Okay, so it's closed on one end. And what do the waves look like on this pipe? So the fundamental frequency is going to have the least number of nodes possible. When the pipe is closed on one end, we are forced to have a node on that end. And the open end has to have an antinode. So the fundamental frequency looks something like this. So there's an oscillation, but the antinode is located at the end of the pipe, at the open end, and there's a node at the end, at the closed end. So what would the second harmonic look like? Let's just copy this thing. And do that a couple more times. Okay, so this is the fundamental frequency, F1. So F2, well, it's got to have a node at the fixed closed end. And it has to have an antinode on the open end, but because it's a higher harmonic, we should be getting an extra node in between. So what that looks like is something like this. Okay, so we get a node, antinode, node, antinode. And we can keep going. If we wanted to go to the next harmonics, we would have to have two nodes in between the ends. So we're going to get a pattern that looks something like this. And next we would have three nodes in between the ends, and so on. So this should be enough for us to figure out a pattern. And then we can have a formula for how the length, the wavelength is related to the frequency. So let's take a look at this first harmonic. So we notice we go from the end point to an antinode. Think about a wave in a string, one complete wave. Looks something like that. And all we are getting is the first quarter of that wave. So in this case, the length is equal to the wavelength over 4. And then the wavelength would be 4 times the length of the pipe, or length of the pipe is here, the length of it from end to end. So for the next harmonic, what are we getting? Well, we're getting, we have a node, an antinode, a node, and another antinode. So we're getting something like that. We get 3/4 of a wavelength here. So the length is equal to 3/4 lambda. So lambda would be 4L over 3. In the third case, the length looks like we have a full wavelength plus a quarter. One full wavelength plus a quarter. So that's 5 lambda over 4. And our wavelength is equal to 4L over 5. This is probably enough for us to see the pattern, but let's go ahead and do one more. The last one, the fourth harmonic, what do we get? We get one whole wavelength and then 3/4 of a wavelength. So that is 7/4 of a wavelength. And the wavelength would be 4L over 7. So we hopefully see the pattern here. We always have a 4L on top, and on the bottom, we have increasing odd numbers, 1, 3, 5, 7. Think of this as 4L over 1. So if we wanted to write that down as a formula, it's not totally obvious unless you have experience with this sort of thing, but let me show you a proposal and let's check it and see if it works. 4L over something that's going to be always an odd number. So we can take 2n minus 1. We call this lambda n. So n, as n increases, the bottom increases by 2. Let's check it out, this formula. So according to that formula, the fundamental harmonic would be 4L over 2 times 1 minus 1. Of course, 2 times 1 minus 1 is 2 minus 1 or just 1. We get 4L over 1. So it works for the fundamental harmonic. For the second harmonic, we would get 4L over 2 times 2 minus 1. So that's going to be 4L over 4 minus 1, which is 3. Again, it agrees with what our picture gave us. And the next one, 4L over 2 times 3 minus 1, that's 4L over 6 minus 1, or 5. And you can see, I think, that this is going to work. Every time the n increases by 1, the denominator is going to increase by 2, and we're going to get odd numbers always because we're subtracting 1 from an even number. So 1, 3, 5, and 7. So this is a formula for a pipe with one closed end. Probably of more importance than knowing this formula or memorizing this formula is having a conceptual idea of how to construct these diagrams. So the closed end gives us a node, always, no matter what harmonic we're talking about. The open end gives us an antinode. And then we go with, in between the ends, 0 nodes, 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes, and so on. Okay, so let's take a look at what happens if we have both ends open or both ends closed. So let's suppose we close both ends. So if we close both ends, we're going to get nodes on both ends. So we know what nodes on both ends looks like. That looks like our guitar string. And that would be the first harmonic, the fundamental frequency. So the second harmonic has to have nodes on both ends, but another node in between. So that looks again like the second harmonic of the guitar string, and that continues for all of the harmonics. So a pipe, if it's closed on both ends, I don't know how we blow air through a pipe closed on both ends, but maybe we just vibrate the pipe with a bow or something. So then we would just see the familiar patterns, and the formulas are identical to the formulas for the guitar string. Okay, so that's not super interesting because it's not really new once we know how these diagrams are going to go. But what about how to do it with both ends open? So if we have both ends open, there we go. Okay, if both ends are open, we have to have an antinode at each end. So how can I have to have an antinode here, and I have to have an antinode here. So how can I do that? I can't just do something like this because that's not a wave. It's not oscillating. Remember, what we are illustrating here by all of these lines is movement, is motion. So the very first pattern we can get that has an antinode on both ends is one that has a node in the middle. That's our fundamental frequency. Well, how about the next one? Well, we again have to have antinodes on the ends. For the fundamental frequency, we had one node in the middle, so now we need two nodes in the middle. So we get a quarter of a wavelength, and then a half of a wavelength, and then a quarter of a wavelength. And if we continue this trend, we would have 3 nodes in the middle and 4. So let's work out the formulas for this case. So in the case of the fundamental frequency, we have a quarter of a wavelength and then another quarter of a wavelength. So that's a half a wavelength when you add them together. So the length is equal to the lambda over 2. And that means that lambda is just 2L. In the next case, what do we have? We have a quarter of a wavelength plus a half plus a quarter. So the 2 quarters add up to a half, and then another half. That adds up to a whole wavelength. So strangely, what we're seeing here is just one complete wavelength. So the length equals just lambda 2. In the next case, we have a quarter, another quarter, and then 2 halves. That winds up being 3 halves. So lambda L equals 3 halves lambda. L equals 3 lambda over 2. And in the last case, we've got 3 halves plus the 2 ends with 2 more quarters gives us 4 halves. So that's 4 lambda over 2. And maybe we can see the pattern here. It's a little bit hard because of the second one, but if we rearrange the lambdas, lambda 2 equals L, lambda 3 equals 2L over 3, and lambda 4 equals 2L over 4. They all seem to have this 2L pattern except for the second one. So we can think of that as 2L over 2 to make the pattern more complete. And then we see that lambda n equals 2L over n. So again, this is actually the same formula as for a string, waves in a string. Doesn't look like the same patterns, but it's the same formula. So for closed on both ends, we have lambda n equals 2L over n. That's our formula from guitar strings, and we got that just by recognizing the pattern. For open on both ends, so for open on both ends, even though the pattern looks different, the formula is the same. What I would say is it's really best if we just understand how to draw these patterns, because then the pictures themselves will give us the right expressions, give us the right values. Rather than trying to memorize, in this case, this is a formula, in this case, this is a formula, in this case, this is a formula. So make sure that you know how to draw these diagrams and extract the formula from the diagram. Okay, let's just try one example. Okay, so suppose we have a pipe closed on one end, has a length of 3 meters. What is its fundamental frequency when air is blown through it? Okay, so since it's closed at one end, let's just kind of get this diagram back in our minds. So what does the fundamental frequency look like? It looks something like this. And that means that the length is just 1/4 of the wavelength, and the wavelength is 4 times the length. So we want to know the fundamental frequency, and we know that the velocity equals frequency times wavelength. Now, this problem doesn't say it, but we should know the velocity of sound in air. If we see a problem on the contest, I would give you this number. But sometimes in the problems in the book, they just assume that you know this number. So the velocity of sound in air is 340 meters per second. Some books say 343. It really depends on things like the temperature and humidity and air pressure and all kinds of stuff. So it's just sort of a approximate number. So then if we want to solve for the fundamental frequency, we just divide the velocity by the wavelength. And the velocity is 340 meters per second, and the wavelength is 4 times the length of 3 meters. You can see those meters are going to just cancel out. And that is 28.3 hertz. You can see we could do similar problems where instead of finding the fundamental frequency, we ask how long should the pipe be to get a certain fundamental frequency. But the key is that for air blowing through a pipe, we need to know the velocity of the sound in air. So again, typically that you can think of that as given. It should be given, but maybe some of the problems assume you know it already. All right, my main focus for you is to be able to draw those diagrams and maybe answer simple questions like what, given the length, what is the fundamental frequency? What are the different what are the different harmonics given the length and the velocity of the sound. That's about it for waves in sound waves in air and strings. There are, of course, many permutations to this. You can take a pipe and you can fix it, you can clamp it in a couple of places, and that would force there to be nodes in different places. And if you go into the physics of music, it is very rich and becomes much more complicated when you have something like percussion instrument, a drum or xylophone. The waves travel in 2 dimensions. They travel in different directions, and the math becomes a much harder, but essentially still the main ingredients are the same.